relatively limited computing power, perhaps depending on the kind of devices you're using. However, potentially a very low latency, potentially a real-time response, potentially a very high bandwidth, and potentially very high energy efficiency. Also, at the edge, you can potentially run an edge device without a continuous internet connection, and you can process data locally and maybe only send a subset of the data, filtered processed data, up into the cloud. So perhaps the key advantages of edge computing for deep learning inference are low latency, real-time response, the ability to run without an internet connection, and the ability to do a lot of processing locally and only actually transmit a filtered, restricted set of data up into the cloud, which might help allay privacy concerns. So, the applications of machine learning and deep learning and neural networks are exploding these days. I'll just mention a few leading applications. So for cloud computing, obvious applications would include recommendation engines for websites, fraud detection for financial transactions, or maybe natural language processing, translating between natural languages. But these applications are just the mere tip of the iceberg in terms of the massive range of applications that are emerging these days. In edge devices, maybe used in mobile phones or maybe for IoT type technology, Internet of Things technology, we have typically a different set of sweet spots. If we're going to implement neural networks on IoT devices, then typically those devices are characterized by the availability of radios, computing resources, and sensors. So for edge deployment, we may be analyzing images, we may be analyzing video or voice, or we might be analyzing the outputs of lower level sensors, such as temperature sensors and vibration sensors. You have a wide range of options available when it comes to the computing power that's going to implement an inference engine at the edge. So you can use microcontrollers, ranging from very small low-end microcontrollers through to high-end application processors, DSPs. GPUs can be used at the edge, although GPUs are not typically favoured for machine learning inference. So just using these general purpose computing devices, we already have a trade-off between accuracy and speed. So low-end microcontrollers are potentially going to offer lower speed and lower accuracy than application processors or DSPs or GPUs. Then we have other more customized options. So we could be using custom neural network accelerators, and custom neural network accelerators could be implemented on SoC devices, or, the topic of this webinar, they could be implemented on FPGAs. So as I've already strongly hinted at, FPGAs can be a great way to implement custom neural network accelerators. And FPGAs in particular can combine both high throughput and low latency within the same device. And also one of the key selling points for FPGAs in this context is that the FPGA fabric is available for implementing other functions at high throughput and low latency. So although you can implement multiple functions on a general purpose CPU or NPU, for example, you can't achieve the same kind of combination of high throughput and low latency that you can achieve on an FPGA device. So let's describe a little bit now the machine learning or deep learning tool flow that's typically used in the context of edge computing, maybe on phones, maybe on IoT devices. So the training for edge devices is very, very close to the training process if you're going to deploy that same neural network on the cloud. You're typically going to be using the same open source training framework. So typically training frameworks, libraries such as Cathay and TensorFlow are going to be used. The same libraries whether you're going to be implementing in a data center or implementing on an edge device. Then for edge computing, we're going to need to perform some kind of format conversion. So there'll be some way to get your trained neural network, both the topology of the network and also all of the weights, out from the open source training framework and into the specific tool flow that you're going to use to program your edge device. So there'll be some sort of vendor-specific format conversion. And all we can say in general right now is that every silicon vendor is going to require this step, and everyone offers a slightly different flow. I'll say a little bit more about the Xilinx flow later on in this webinar. Then we're going to focus in on the weights, the trained parameters, with a process that may consist of pruning or quantization or compression. So we're focusing here now on the weights that have been trained in Caffe or TensorFlow or whatever high-level framework we're using. And then specifically for deployment in an edge device, what we're going to try to do is to minimize the footprint of our neural network, and in particular minimize the amount of memory that we need to store weights. Ideally, we want to have all the weights of our neural network implemented on chip so that we can avoid relatively slow and high power off chip memory accesses. So the goal of this step is to try to minimize the memory footprint of our weights. And so we've got a number of tools at our disposal there. With pruning, what we try to do is to set any near zero weights to zero. Let me talk about pruning in a little bit more detail, because it turns out that Xilinx actually provide for you some state-of-the-art pruning tools. With pruning, what we're doing is to take weights in our fully trained network, and if those weights are pretty close to zero, we're setting them to zero. And having set the weights to zero, we can then reevaluate the performance of our network. So if we look at these two dashed lines here, these two dashed lines show the result of two slightly different networks and two slightly different training algorithms by pruning weights that are close to zero. And you can see here that we start seeing an accuracy loss when perhaps something like 50% of our weights have been set to zero. But we can get up here to maybe, a 67% of our weights have been pruned away, and we've still got an accuracy loss of just 1%. And even with 80% of the weights pruned away, or perhaps closer to 90% with this slightly different training algorithm, our accuracy loss is still less than 5%. So you can see here that you can actually prune away a substantial proportion of the weights within a neural network, which has the advantage of both simplifying the network and also minimizing the memory to store the weights, and still achieve a relatively low accuracy loss. But we can do much better if, having pruned the network, we then start iteratively retraining the network. So the next two lines here, the green and the yellow line, shows the accuracy loss if we prune our network and then retrain it, having pruned the network. So we're pruning weights that are close to zero, and then we're retraining that neural network. And you can see how here we're getting spectacularly better results. So even after 80% of the weights have been pruned, we've still got negligible accuracy loss. And we have to get up to 90% of the weights being pruned before we really see a significant accuracy loss. And if we then go ahead and iteratively prune, retrain, we get this curve shown in red here. So this is the result of iteratively pruning and retraining a network. And you can see here we've got something like 95% of the weights pruned away before we get a significant drop in accuracy. So pruning can be a very, very significant technique in simplifying a network and minimizing the amount of memory required for the weights. And as I've already hinted, Xilinx do a pretty good job at this. Then might come quantization. So quantization is another technique that's used both to reduce the memory that we need to store the weights of a neural network when it's deployed in the field, and also to minimize the amount of hardware and simplifies that hardware. And again, this can be very significant for deployment in FPGA devices. So training within frameworks such as Caffe and TensorFlow, PyTorch and Keras is universally done right now using 32-bit floating point arithmetic. But we don't really want to be implementing 32-bit floating point arithmetic within our FPGA devices if we can use a simpler form of arithmetic. And it turns out a really good choice that's pretty much universally applicable is to quantize our 32-bit floating point numbers to 8-bit integers for deployment. We can actually be even more aggressive than that and quantize our activations and our weights of our neural network down to even smaller integers, but 8 bits is perhaps the quantization that's most typically used right now. So if we were going to deploy our neural network in a Xilinx FPGA device and actually have that device deployed at the edge, then we might do some pretty aggressive pruning by setting near zero weights to 0, retrain our network, quantize our network to replace 32-bit floating point numbers with 8-bit integers, and then maybe do some further compression on the weight matrix, again depending exactly how we're going to deploy our device and what kind of device we're going to use. And finally, we're going to perform some engine-specific optimizations. And these optimizations are going to be fine-tuned and customized depending on the kind of inference engine you're using. Again, whether it's a microcontroller or a CPU, a DSP, or an FPGA device. So in the case of FPGA devices or other devices, we might perform some operation fusing or layer fusing, where we fuse and simplify the operations in order to make maximum use of whatever's available in our target implementation device. So FPGAs can make use of very aggressive operation fusing because FPGAs have a very high degree of flexibility in terms of the core calculations being performed by the device. Also, we're going to want to optimize the use of the memory on device, again, so we can make sure that we can fit all of our weights, if possible, on the physical device. So we have to do minimal access to slow off-chip memory. So let's take a look now at machine learning and deep learning in FPGAs in particular. And again, as I said at the outset, I'm not really going to do a deep dive into FPGA technology. And the reason I'm not going to do a deep dive into FPGA technology is I don't need to, because what Xilinx have done is to abstract away a lot of the details of the specific device and provide a much higher level user interface. So what we can do pretty much is to train up our networks in our preferred framework, TensorFlow or PyTorch or whatever it might be, and then take that trained neural network into the Xilinx tools and have the Xilinx tool manage the whole back-end flow through to our chosen FPGA or ACAP device. Before I look at that Xilinx flow, let me just recap some of the advantages of FPGAs in particular when it comes to deep learning and neural network inference. The first advantage I've already mentioned. FPGAs give a great combination of both high throughput and low latency when compared to GPUs or CPUs. It's possible to get relatively high throughput using big GPU or perhaps multiple parallel CPU devices, but FPGAs are unique in terms that they give a combination of both high throughput and low latency by taking advantage of the features of the FPGA architecture. Also, as I've already mentioned, FPGAs have the advantage that they can accelerate other performance critical features, not just the AI. And this is a great benefit of FPGAs compared to other custom accelerators. So you can buy these days custom neural network accelerators, maybe implemented within an SoC device, and they may give great performance for the neural networks, but they can't accelerate other performance critical functions, whereas FPGAs are just great accelerators both for neural networks and for other functions. Then the final advantage of FPGAs is because the FPGA architecture is fully programmable, versus a fixed accelerator, the architecture can actually be optimized and customized for the specific details of the neural network being implemented and to reflect innovations in neural network architectures. So any innovations in neural network architectures, and the neural network architectures are being changed and improved all the time, can be taken advantage of within the FPGA architecture. So now let's talk about Xilinx in particular. Xilinx Vitus is a software development platform whose goal is to make Xilinx FPGA technology and ACAP technology accessible to software programmers who don't have a lot of FPGA implementation expertise, who aren't expert hardware designers. And Vitus AI in particular makes the Xilinx devices accessible to software engineers who have a relatively high level knowledge of how to program neural networks. So what we can do with Vitus AI is to start off with our favourite deep learning frameworks. So Vitus AI supports frameworks such as TensorFlow, Caffe and PyTorch. Convert neural networks from those frameworks into the Vitus AI development kit, and then have Vitus hide and abstract away most of the implementation detail. So we barely need to know that we're implementing these networks on an FPGA or an ACAP at all. We can take advantage of a whole range of tools provided by Xilinx in the Vitus AI development kit. So the optimizer, quantizer, compiler, runtime, library and profiler. Then XRT, which is Xilinx runtime. This is a runtime system that again is independent of the precise implementation technology that we end up using. When it comes to implementation, Xilinx provide a number of predefined DPUs. DPU is a deep learning processor unit. So the DPUs are predefined, customized, optimized architectures that are optimized for implementation within Xilinx devices. And this flow supports deployment both in data centers using Alveo devices and also on the edge using Zinc devices. Let me just mention a few of the tools in this toolkit in a bit more detail. So the Xilinx Vitus AI Optimizer performs the pruning task that I referred to previously. So the AI Optimizer takes a neural network that it's been trained using 32-bit floating point numbers and then performs pruning to minimize the number of weights to produce a pruned network, still using 32-bit numbers. And using the Vitus AI Optimizer, we can prune up to something like 90% of the weights for deployment in edge devices. The AI Quantizer performs quantization, just as I referred to previously. So we take our neural network, trained up in 32-bit floating point numbers, and then perform quantization to produce the network, the model that's actually going to be deployed in the edge device or indeed the cloud device. And that's going to be using 8-bit integer numbers. So as I said previously, 8-bit integers are regarded as a great practical compromise. We typically lose little or no accuracy in quantizing 32-bit floating point numbers into 8-bit integers. If we actually want to run the Vitus AI Quantizer, turns out we are going to require a calibration dataset in order to calibrate the accuracy of the quantization process. So we can use this calibration dataset to check the precise impact of quantizing the network. And we typically find that the accuracy loss is very, very low or negligible. Then the Vitus AI Compiler performs optimizations on the neural network. It tweaks the implementation of the neural network to optimize it for the FPGA or ACAP technology that's being used. So it might perform optimizations such as operation fusing or layer fusion, the precise scheduling of instructions to make optimal use of the architecture, and to optimize the use of on-chip memory, so we fit as many weights as possible into the on-chip memory. The Vitus AI Library includes the predefined DPU architectures and the runtime systems. So we start off with Vitus AI Runtime, which is a generic runtime system that's applicable for deployment both in cloud devices and edge devices. Then the Xilinx Runtime Library that's going to do the very low-level runtime scheduling once our inference engine is deployed in the field. And then the neural network architecture will be mapped down onto one or more DPUs, deep learning processor units. The DPU architecture started out life in edge devices, but Xilinx have now extended and generalized this architecture so that in the latest generation it's applicable both to edge devices and in the data center. So there are variants on the DPU for deployment on Sync devices, both Sync 7000 and Sync 7000 and Sync Ultra Scale, and very new variants on the DPU for deployment on Alveo boards in the data center. And the beauty of this kind of flow is that most of the details of the target device are hidden from the user. So really you do just need to start off with knowledge of how to run your chosen open source training framework. You need to understand neural networks. You need to understand how to train neural networks. You need to understand how to curate your data set for training the neural network. But most of the back-end flow you can leave to the Vitus AI development environment. So, a few final remarks. In general, although deep learning has absolutely made it out into the field now, it's also still a research topic, and in some ways it's still the Wild West. So there's still a lot of research activity going on. There's a lot of science being done around neural networks and deep learning. Although some applications have certainly made it into the field. There are some real sweet spots such as image processing and object detection, which are absolutely commercially applicable and very, very widely used right now. However, it's still a very new field, and all of the tools and flows of products are still pretty new. So indeed, the Xilinx Vitus AI development environment is a pretty new development environment. Whichever platform you choose to use, whichever implementation engine you choose to use, whichever inference engine you use, whichever training framework you use, you do need to know what you're doing. You need to understand that data is critical and central to this flow. You need to understand how to collect and curate the data sets that you're going to be using for machine learning or deep learning. You need to understand how to select and optimize your neural network architecture. And then having selected, optimized and trained your neural network architecture, you can then hand that off to your silicon vendor, such as Xilinx, and use the particular software flow provided by your silicon vendor to actually implement the inference engine. But in general, you certainly need to know what you're doing. And you're going to find, as you know what you're doing, that experimentation and iteration are essential. Training neural networks really is an experimental science. A lot of iteration and trial and error are involved, the data being central to that whole process. So you absolutely need to know what you're doing. And of course at Doulos we can help you with that. So we offer a 5-day hands-on training class, Practical Deep Learning, and this training course is very in-depth training to cover both principles and practices of deep learning, all the practical implementation details of how you can implement neural networks using your chosen training framework. We actually make use of TensorFlow and Keras within the Practical Deep Learning class. We also provide a really solid introduction to both training and inference and all of the options you have at your disposal as you come to implement your inference engine. So check out this URL if you want further details. So at Doulos we provide a very wide range of training classes worldwide, including training in embedded software, ARM technology, FPGA hardware, SoC design and verification, Python and deep learning. So check up our website if you want further details. Do feel free to ask any further questions you may have using the GoToWebinar training interface, and we'll stay online answering your questions as long as you're asking them. So thank you very much for your attention, and bye for now.
Excellent. Many thanks to John for that presentation, and thank you all for attending. As John mentioned, we have a full 5-session deep learning training course live online. And as you can see, that's available to access worldwide, with courses starting on the 29th of November for Americas and the 13th of December for Eurasia. You're also welcome to leave us a note to contact you about that in a post-webinar survey if that's of interest to you. So, as soon as possible, we'll email you the link to the stream recording of the webinar as well as the Q&A log. But we're still online now in a text chat to answer any final questions you might have. And finally, please could you also complete the survey that pops up when you close the webinar window. And by all means, use this to get in touch with our team for more details about any related training requirements you may have. So many thanks again for your interest and attending today. We hope to see you soon. Bye for now.